All right, engineering students, let's proceed from where you left last time. So the first part of the revision session, we're looking at uh, the standard way in which questions on nomenclature, they are actually, uh, the approach should take that the standard way is to be given a name of an organic molecule, which is not the correct name, but based on that one, you can be able to reconstruct the structure with all the functional group and stereochemistry for the E and the Z and the rest. And then from there, you come up with a proper IUPAC name. So um, some of the things that have not escaped, and this one you're going to see in every engineering paper, because we know that you're dealing with engineers, and engineers like calculations. So calculations you cannot avoid. There needs to be some things dealing with calculations. As such, though I think I'll be able to communicate to your class reps, uh, you need to have a calculator in an exam. A what? A calculator. Yeah, a standard calculator in an exam, and if possible, even a ruler. Sometimes you may need to do some things to try to draw a table and the rest, and you just want to avoid putting some lines which are not straight. Yeah, so you need what? A calculator, a ruler, and if possible, even a rubber and even a pencil to be able to do the calculation later, and then probably put the proper calculations and the rest. So in the course of in this course chemistry 2, organic chemistry for engineering students, there are calculations uh, in three topics. Yeah, uh, energy. You're talking about fuel. In this case, you're talking about fuels. Yeah, fuels. You're dealing with energy calculations. You cannot avoid those, and also uh, there is another topic which I would really emphasize on you going back to, and this is on determination of empirical and molecular formula. There are very good calculations there on determinations of empirical. You're talking about empirical is the simplest formula in which a structure can exist, but that does not mean that it exists like that one. So the actual formula is the so-called like the molecular formula, but the empirical, it gives the simplest manifestation of the structure. And in this case, uh, these calculations on the empirical and molecular formula uh, is going to give you an overview of how to calculate. Now, there are questions dealing with fertilizer, and I'm going to mention something about that. And the other part of the where the calculations are on electrochemistry, where you're being told to be able to determine the expected EMF. EMF is the potential of a of a of an electrochemical cell. In this case, you'll be dealing with a cell which is producing voltage, which is the galvanic cell. You know, there are two types of cells. There is the galvanic, and then there is the electrolytic cell. The electrolytic cell is where you are giving the voltage, and then you're affecting a chemical reaction. But in this case, you are saying you are doing certain chemical reactions, and then they are producing a voltage. So in that case, you can be asked to be able to determine the voltage that's going to be produced. So those are the calculations that are given. Now in this case, I've just tried to come up with one though a simpler approach is given in the empirical and molecular formula, but of late we've been trying to come up with uh, with uh, uh, with structures which may not be simple. But for example, like in the one which is shown like in that lecture is just giving something like a butane. But in this case, I've just tried to take a typical organic compound. Like this one, it is branched, and doesn't contain only carbon and hydrogen, it contains even oxygen. Yeah. So like in this case, you are just told, like for example, there is 9.8 grams of uh, of 3-methyl pentan 2-ol that it is burnt in oxygen. And based on that one, you're just told, based on that one, you're supposed to do what? To determine the exact amount of oxygen that was required for the combustion, and then the exact weight of carbon dioxide produced, and also for the water produced. Yeah. So based on that information, there's something that is normally given as a standard in examinations, and that is, uh, though if you know it often is okay. Uh, the mass, carbon is 12, hydrogen is 1, oxygen is 16. Yeah. So you need to know that one, but it's normally given uh, somewhere probably at the beginning in the instructions. You can see that carbon is 12, hydrogen is 1, oxygen is 16. That's the information that can be given. So based on that one, the rest is for you to use what you know to be able uh, to get the information. I just try to give an example here. So based on this one, you'll be able to come up with such a structure. It's a pentatone, 1, 2, 3, 4, 5. It's 5 carbon atoms. There is a methyl group on carbon number 3, and there's the alcohol group on carbon number 2. So based on that one, you come up with such a structure, and that is meant to give you the structural formula or the molecular formula. In this case, it is 6 carbon atoms, and then 10 hydrogen and 1 oxygen. Yeah. So I think even though I've put here, but I've just tried to balance here, uh, uh, but but these figures, I think you can be able to really derive uh, because the first thing is, before you the, let me just delete this one to show where you actually start. Yeah. Before you uh, because you can look at that formula and just say, how do I start balancing and the rest? It's quite easy. Everything is given from a lot of things are given from this formula. For example, this formula is telling you uh, is C6H10O. So that tells you that on this other side there are how many carbon atoms? 6 carbon atoms. So in this case, I'm going to put a 6 here because it is the balance of them. I mean, atoms are not destroyed. Yeah. So if you've got 6 carbon atoms, then you put 6 there. You see how you come up with the 6 for the carbon dioxide. And then it tells you there are 10 atoms of hydrogen. Along this side, what exists, there are 2 hydrogens for 1 oxygen. So if there are 2 here, then I'm going to put a 5 here to make them 10, similar to what I have here. So you've seen how we've come up with those coefficients 6 and 5. And then based on that one, then you know, then you count here. The what? How many oxygen atoms are on the right? In this case, 5 times, or so that is 5, and then 6 times oxygen is, in this case for CO2 is times 2. So this is 12, 12 plus 5, that is 17. So you know you are actually producing 17 oxygen atoms. And then what do you have? What do you have on the left? Because you want to see the coefficient which you have here. So if this is 17, and then the on the left there is a compound containing oxygen. It contains how many oxygen atoms? 1. So if it is 17, then I'm going to minus 1. It means that the remaining atoms are 16. Yeah. These are 17, and on this side there is 1. So it means that so the remaining oxygen are 16, and if there are 16 and this oxygen is existing as a dimer, then I'm going to put an 8 here. You understand? So that's how you are going to balance. And then something which you also need to know is that the number of moles is given by the weight divided by the relative molecular mass. Yeah. So that in this case, if at all it is 9.8, and from the relative molecular mass given by this, uh, carbon is equals to 12, hydrogen is 1, and oxygen 16. I was just doing these calculations here to show that carbon is 72, hydrogen is 10, and then oxygen 16. I come up with a number of 98. So if we're told you're dealing with a 9.8 grams, then I'm saying that 9.8 divided by 98, that is 0.1 moles. Yeah. So from this information, you're going to say that that you know in a standard way that 1 mole of alcohol reacts with 8 moles of oxygen to give 6 moles of carbon dioxide and 5 moles of 5 moles of, or 6 moles of carbon dioxide and 5 moles of 5 moles of water. Sorry. Okay. And then from that, then you construct this table. Yeah, because this table shows you that you are doing your work in a structured manner. So just put the the compounds on the first column, the second column relative molecular mass, the third one as the mole, and then now the information that you've been given. In this case, you just know the weight of the starting material was 9.8. Yeah. And then now, based on this formula here, then you know oxygen is 16. Uh, what carbon dioxide uh, is what 44. Oxygen, I mean water is 18. And from what you know here is that based on here that 1 mole of this, then you know if you're having 0.1 mole of the alcohol, it's reacting with 0.8 moles of oxygen to give 0.6 moles of carbon dioxide, and then 0.5 moles of water. And then based on the fact that the weight is moles multiplied by the relative molecular mass, uh, I've not done this calculation, but I think from here you just know uh, 16 times 0.8, you know, with a calculator, you'll be able to get the grams. Water, 18 times 0.5, that one, I think that one is now clear. That is 9 grams, yeah? Here, so here I'm going to put 9, yeah? So you can be able to do the other calculation, 44 times 0.6, and then so you'll be able to put the relevant information here. Yeah? So this is one way in which calculations on combustion are set. So I think I'm just going to pause a bit, and then we look at the the calculations dealing with the what do you call it? Like the bomb calorimeter. That's the other part of the calculation. I'm only dealing with calculations aspect. Yeah. So let me pause a bit, and then we'll proceed from there. All right, engineering students, let's just proceed from uh, from where I've left. Now, in this case, I'm looking at the calculations dealing with bomb calorimeter. Dealing with what? Bomb calorimeter. Now, a bomb calorimeter, we've got a sample in the Department of Chemistry, but I may not be able to bring it here. But what it does is for determining the calorific value, the energy content of fuels that you may burn, mostly for non-volatile liquids and for solids. So in this case, if it is not all that volatile, then the liquid you can be able to bring it up as a you can be able to put it as a liquid. But if it is very volatile, then it will be moving around, and it will be a bit be hard to really handle. So you put your compound in something called a crucible, which cannot be affected by sudden change in the temperature. It means that a crucible should be made of a substance like what? Like porcelain and the rest, and everything else, yeah? So this is just a typical example, but in your notes, you'll be able to, in your lecture notes, you'll be able to see the exact setup for a bomb calorimeter. So this one I just put a simplistic way, but it has a way of where you can be able to put in oxygen under pressure. So put a lot of oxygen knowing that you put excess, and then it has a heating element, probably made of tungsten or maybe platinum, to which once you turn it on, excuse me, it becomes red hot, and that temperature is sufficient to ignite the compound in yeah, in oxygen. So there's the violent combustion. So you just if you can be able to listen, you'll be able to hear something like a small boom, which is what scientists are going to say. Hey, this thing is behaving like a bomb. So, but just uh, a restricted way. So that heat which has been produced by the compound which you have burned, some of it or significant amount of it is going to be absorbed by that apparatus that contains the crucible, the element, all those things. Uh, uh, Sometimes you can be able to uh, there are ways in which two ways to approach to this one. One is that you can be told there is an experiment in which you're going to do to be able to determine what the calorific value for that the calorimeter constant. It means that you're going to burn a standard compound, which in this case is normally benzoic acid, which has got a known heat which is going to be released. And then from there, you can be able to determine the calorimeter constant. But in this case, let's just say you've just been given that value, 900 joules per, uh, not calories, but per degree Celsius, yeah? Excuse me. So the other information which you can be given is the specific heat, excuse me, the specific heat capacity of water, because the other, well, and this is what you're going to really be measuring. Once you've got, once the combustion has started, the you start monitoring the rise in the temperature up to when the temperature cannot rise anymore. If you're going to do an experiment, and hopefully, I'm just trying to campaign so that this experiment can be given to future students. That means that we want to see whether they can get something like 5 or 6 or maybe 10 bomb calorimeters as opposed to one in which you have, and therefore you'll be able to see how you can be able to determine to do this experiment yourself. But what happens is that usually plot a graph that you do until you ensure that before you ignite, the temperature is actually stable. Then when you're going to ignite, there's the increase in the temperature until when it cannot increase, and then you get a flattening here. Yeah. So this range, yeah, from the when it was stable to when it is rising here is that uh, rise in the temperature. Yeah. So that's what you record here. So this is time elapsed. It could be minutes, seconds, or hours, and here is the temperature in degrees Celsius. Yeah. So you're going to plot something like that, and then based on that information, you'll be able to put the information on the calculations here. So what you're saying is this: is that the weight, uh, the okay, let me say heat given of in this case, you could be asked if it's a pure compound, which which sometimes can be given. Then in that case, you're going to be told to determine the energy in something like kilojoules per mole. So the first thing which you'll have to do will be to determine the energy given off in kilojoules or maybe megajoules. It depends on the unit, or maybe megajoules, maybe kilojoules per gram. Yeah, and then from the grams, gram stands gram is equals to what the moles times the relative molecular mass. Yeah. So what I want to say is that uh, this is what you want to determine. Now that one it will be equal to to the heat absorbed. And this heat absorbed is equal to the heat absorbed by calorimeter plus heat absorbed by water in in the jacket, yeah, in the jacket, which is holding uh, the the calorimeter, in which the calorimeter is immersed in. So uh, so the one for the calorimeter is normally easy. It just means you're just going to take the calorimeter constant, and then you multiply by the change in the temperature, and then you're going to get the first unknown, yeah, that the heat absorbed by the calorimeter, which will be, in this case, if it is joules per degree Celsius, then if you're going to multiply by the temperature rise, then it will give you the energy absorbed by the calorimeter in joules, yeah. And something which I need to say is that please, please, please do not uh, what uh, do not approximate the decimals until the very end. Otherwise, these calculations you can be able to get it wrong. So, for example, if you're just going to get something like maybe 900.2345, probably you may need to reduce it to up to probably 5 joules, or maybe if I say this is going to be 9050 point whatever. So those decimals, you still leave them the way they are, yeah, for the time being. And then so that's the first unknown. The second unknown is the heat absorbed by the water. And this is given by the mass of the water multiplied by the specific heat capacity times the change in the temperature. Now, what does this calculation imply? That you've been told you're dealing with something like 1 liter of water, that it assumes that 1 liter is equivalent to 1,000 grams or 1 kilogram. Yeah, but you know that one is only true for 4 degrees Celsius, that the density of water is not exactly 1.1 gram per mil, but on this one, I think you can now assume that one to be density to be 1 gram per mil. So therefore, from the 1 liter, you'll be able to say probably you've got 1,000 grams for, that would be the specific heat capacity you are given, and then the temperature change. Maybe that one you can get, maybe another, maybe I say maybe it's 18,050, maybe maybe 587, yeah. So that one will give you, maybe you are going to get, maybe this is 27,100. I'm just trying to give point, maybe 9. I'm just trying to give something like that, yeah? Are you okay on that one? So in this case, this is equals to the energy which has been absorbed, yeah? Heat which has been absorbed. So now that one will be equal to the energy, to the heat which has been given off. And then now, you're just going to say this energy, which is what has been given off. It has been given off by, maybe it can be something like maybe 2.5 grams, 2.5 grams of the pure compound. It gives that energy. So if I'm going to get maybe something like that 27,000.999 over now the 2.5, I'm just going to get this one. It will be the energy, it will be 27, whatever it is. It may be something like maybe I'm just trying to give example, yeah, maybe 17,000 joules per gram. You understand? Yeah, I'm just trying to give an example, whatever it is with the decimal. Then from there, this has been the energy given per gram, and then now you now know the gram or the weight is equals to the moles times the relative molecular mass. Also, it means that the relative molecular mass is equals to weight over the moles. Yeah? So this means that from the weight of the pure compound, you'll be able to determine the relative molecular mass, and then you're going to put the moles here times the weight, and then from there, so you'll be able to now get to convert from the joules per gram to the joules per moles. And then if you're just being told to be in kilojoules, then you're going to divide by 1,000 to get it in kilojoules or megajoules, whatever it is, yeah, per mole. And then on the final answer, that's when you can approximate to probably 1 or 2 decimal places. But please do not do it at the beginning. Otherwise, those approximation of the decimals towards the end, they add up to very significant figures. Yeah. So this is one aspect of the questions, the way they come. In this case, I've covered on the combustion. So I'm just going to stop there, and then sorry, and then in a short while I look at I think the other two calculations. They are not as significant as the ones on the fuel. So we'll be talking about like the fuel calculations on fertilizers and the ones on the electrochemistry. Yeah. So I really hope you've enjoyed this part of the revision. I'll just try to give an example of that one. It may not be clear from the notes. So I'll just stop there, and then in a short while we'll proceed on with the next part.